This is Lab 1 Constant Velocity for Physics 2211. So, the purpose of this lab is to compare the observed motion of an object traveling at constant velocity to its predicted motion using a computer model. My object in this case is going to be a whiteboard pen. The observed position we're going to get using a tracker app and the predicted position using a GlowScript code. This lab will aim to demonstrate Newton's second law. So, the principles, Newton's first law. Well, this is going to be very important for our lab because we're going to be assuming that there's no net external force acting on our object, meaning that it will be in constant motion the whole time. So, its velocity should be the same at every single data point, every time. So, Newton's second law. This is also very important because from this we can derive the velocity and the position update formula, which we are going to be using. So we start off with the definition, work our way down using the fact that momentum is mass times velocity. We get the velocity update formula. We wrote it here, very important. And also we've got our position update formula where we're going to be using velocity average. And V average is going to be final velocity plus initial velocity over 2. Since F net is going to be 0, our velocity at every single data point will be the same. So the setup. The system is the pen, surroundings everything other than the pen. The assumption of our experiment is that the net force is zero, i.e. no forces are acting on the system. But an initial force will be applied on the system, so the system will move at constant motion. Otherwise, the pen wouldn't move, just remain in place. Initial conditions, time equals zero, position equals zero, and our computer model is going to be generating using a GlowScript code. So this is the preview. As we can see, the computer generation code over predicted the position at every single time point, but the gap got larger as time got bigger. Let's see why this happened. So, the procedure. 1. We're going to record a video of a pen rolling at constant speed in a straight line perpendicular to the camera angle, meaning along the x-axis. We're going to use a software tracker to determine the pen's position frame by frame. Then we're going to use GlowScript code to create a computational model of the pen's predicted motion. And then we're going to use Excel to compare the actual motion and the predicted motion in a position v time graph. We're going to make So here you can see the motion of the pen moving across in this video, and one important thing to state I do have to talk about is that for some reason my tracker app started recording approximately 0.5 seconds before the pen entered into frame. So here we have position starts to increase, but only at 0.5. Now obviously we need the initial conditions to be time equals 0 and position equals 0 to compare the GlowScript code and the tracker app. So when I approached my professor in the lab about this, he said just take this data point, set it to time equals 0, so you have the same starting conditions. Okay. So, our tracker analysis. Well, these are our first data point, our second data point, and this is in order to find the initial velocity. So we can easily find our change in time, our initial position, final position, and here we have that our initial velocity is approximately the average velocity between these two data points. Now, in reality, because there is a decelerating force here, the first position is going to have a greater velocity, the second a smaller one, but we're going to assume it's about the same, so we find out the average velocity, which is of course just initial velocity at this point using this equation, and we get this result. So, our computational model in GlowScript, well, the mass of the ball we set to 1, which again has no effect because our F net is 0. As you can see here, this whole thing is 0. So we have our initial position, our initial velocity, our FPS of my phone camera, and we use our velocity update formula and our position update formula that we derived earlier. So this is our output as expected. The ball is going to move in constant motion along the x-axis towards the right. So this is the observer's computer predicted data. So the computer predicted GlowScript overshot at the position at every single time point, but the gap got larger as time went on as compared to the tracer. Let's see why this is. So most obviously errors. 1, we're tracking at an angle, and as you can see, yup, it's an angle. So the ball is not going along, or sorry, excuse me, the pen is not going along the x-axis, but it's going at an angle. Now this is just because the camera angle is filmed wrong. That's part of human error. So next part is rounding error in calculations. Yep, so this is important. This is creates some small offsets, but it shouldn't have too much of an effect. 3, human error. People can input, stuff into spreadsheets wrong, write code wrong. It happens. But 4, and most likely, is going to be outside forces, where Fnet was not actually 0. So what if the x-axis was flipped? Well, the points of data would be negative, causing the slope of the graph to be negative. The magnitude of change would be the same, so rate would be the same. And it would just appear as if the pen was rolling backwards instead of forwards. So what does this mean? Well, since the computational model overestimates the position of the pen compared to the tracker, especially at increasingly greater times, the system must have a net force not equal to 0. So there must be a net force acting on the system. This net force must be creating some deceleration in the pen's motion, meaning the force is acting as a resistive force to this motion, so opposite in direction to the motion of the pen. Well, and the force is going to be most likely friction from the surface and air resistance. However, it could be anything, even including air conditioning or someone, blowing with their mouth. All right, thank you.